Bias-Variance Trade-Off. Bias-Variance Trade-Off refers to the balance between two types of errors that a model can have. The two types of errors are bias error and variance error. So whatever types of errors you had seen till this point, let us take sum of squared error or something, that in effect is composed of bias error and variance error. Let us understand what these two types of errors are and how they originate. Let us understand bias error first. Bias error measures how much the predictions of a model differ from the actual values. That is, initially when you're training a model, you have the values of x and y. So x is the independent variable and y is your target. So the values of target you already have for the data that you're having. Using x, what will you do? You'll try to approximate this y. While approximating, y cap is the value that you get. Let's say you have some equation like w0 plus w1x or something. This is y cap. So you're approximating x using your linear regression function, and that approximation is y cap. There will be an error which is the difference between the values of y cap and y. While you are approximating, there will be a difference. This difference is what finally adds up to bias error. Let us understand first graphically. This is my graph. This is my graph, and let us say my underlying distribution is this. Let us say from this function I derived all the points. From this I derived different data points. So the xy coordinates that I provided, that is originating from this particular function. Let us say these are the points that I have. So the points will be slightly here and there from the actual function. Every point won't be exactly on the line, but there will be some points which are on the line as well. So let us assume this is what I have, okay? In this case, I'm trying to approximate. Let us say I have a linear regression function, and the best approximation that I was able to make, let us say, was this. This is not a very good approximation, but this is only what my model was able to make, okay? In this case, if you take any particular data point that you have, let us take this data point. There is a difference between what I found and what is the actual data point. This is the difference, right? Actual y is here, the data point, but what I found is on the blue line. It is here. So the difference between these 2 points, this is what you call as bias. So having high bias means model is making strong assumptions about the underlying data, which results in underfitting. In general, high bias means the model is too simple, because whichever data point you take, there will be a difference between what the model has found and what is the actual data point that you provided to the model. So this difference, if you average this difference out on all data points, you will get the bias error. So where is it important for you to understand this? Because having bias error means the model was not able to study your data properly. Because if it was able to study your data, what will happen? Whatever points you have, the model should be able to go somewhere near these points. But if it is not able to track your points at all, that means bias is higher. Whatever is the actual data that you provided, the model is not able to cope up with that data. It is having high bias. Let us understand variance. What is variance error? Variance error measures how much the predictions of the model vary for different training sets. See, you may feel these are similar, but these are totally different concepts. In fact, you can say bias and variance are opposite to each other. This will be clear for you when I show this graphically. That is, when I say measures how much the predictions of the model vary for different training sets, the point is for different training sets, how much do they vary? That is what variance looks at. That is, let us take the same case and understand it. Presently, I showed you when I trained on one particular data set. Instead, let us take 2 data sets. I'm having this function. The underlying function remains the same. This is my underlying function. This is my underlying function. And let us say the training data, I have two sets of training data. One I'll denote with green color. So with green color, this is one set of training data that I took for this model. Okay. I got this training data for the model. This is one set of training data that I got. Let us say there is one more set. Let this be one more point. Okay, these points I obtained from our function only, which is the original function is in yellow color, the yellow function. From that I obtained few data points using which I'll train my model. So the blue set, that is my first training set. Let us say I have one more set. Let us say it is red set. So the red points, this is my second training set. I'm going to train the model on both these training sets. Okay. So this red points, this let's say corresponds to another training set. Okay. In this case, if the model is having high variance, what happens is it will understand the data very well. But the problem is it will overfit to this data so that when I look at the function generated by one training set and when I compare it with the function generated by the other training set, the difference will be huge. I'll just show it with an example. Let us say if with this red data, this is what is approximated by my function. Okay. Using these red training sets, this is what my function approximated. So in this case, what is the bias error? In the red case, if you see the bias error, it is 0, isn't it? The bias error, if you see, the red case is 0 because whatever be the point, through all the points, my generated function, the red colored line, that is passing through each of the data points that I provided, which means there is no difference between the predicted value and the actual data point, which means bias error is almost 0 here. But variance is high. I'll show you where variance is high. See, I'll put y cap here. Okay, let me draw the blue line as well. This blue is the function that I found, the regression function that I found by making use of my second set of data set, which is colored in blue here. So when I gave the blue points to the model, what did the model try to draw? This is what I'm trying to show you. So let us say the model found something like this. This is what, let's say, my model found with blue lines. So with the red lines, if you just see the data point that I provided, the model is just perfect, right? There is no error at all as far as bias error is concerned, because whatever data point I gave, the model learned it perfectly. The same is the case with the blue here. Whatever blue points I gave, the model learned all those blue points perfectly and fit it perfectly. So if you, at any point, let us take this point, if you see the difference between the actually given data point, which is this, and what my function found out, which is the blue line, both are one and the same, both coincide, which means bias error is 0. What is variance error here? When I gave two different data sets, one is blue data set and the other is the red data set, with two data sets which are generated from the same function. The yellow line here, this is the function from which I generated both data sets. So two data sets generated from the same function is giving two totally different regression functions. This is what variance is. That is, it measures how much the predictions of a model vary for different training sets. I gave a blue training set, then a red training set. Both are for the same underlying function, but when I gave two different training sets, the generated function is totally different. This is variance, the variance between what is generated for one training set and the other training set. Bias is what is the difference in the prediction for each point if you compare with the actual data set. That is bias. So what you have to understand is, as far as variance is concerned, if variance is very high, that means the model is overfitting. If the bias is high, that means the model is underfitting. What did we draw in case of bias? Let me draw that line as well. Let me take green color. In case of bias, I had shown if it is having high bias, the model found out something like this, the green line. The green line is what it found in bias case, and the blue and red are the ones it found in high variance case. This is the difference. So in short, the model is too complex. In that case, variance error will be high. Okay, this is complex model which overfits. In case of high bias, it is underfitting, which means the model is simple model which underfits, that causes high bias. A complex model which overfits, it causes high variance. The next question is, why is this called a bias variance trade-off? I understood there is bias error, there is variance error. Why do we call it a bias variance trade-off? The reason is very simple. As you try to decrease the bias, if you are trying to decrease the bias in the model, automatically variance will increase. This is kind of an after effect. Whenever you try to decrease the bias, automatically variance will increase, because how is the bias caused here? When your plotted line is very distant from the actual data point, that is when bias is increased. What will you try to avoid bias? You will try to take the line as close as possible to the data point that you plotted, right? You will try to pass it through the data point. If you pass it exactly through the data point, what will happen? It will overfit to this particular set of data. If you give any generalized data set again, it won't fit well. In case of the blue and red lines that we saw here, because the blue graph, the blue one fitted perfectly with the data. While if you see the green one, it didn't fit perfectly at all. That is having high bias. So it's called a trade-off because whenever bias increases, variance decreases. Same if whenever bias decreases, variance increases. So the problem is, if you have low bias and high variance, in this case, your model is complex model. The models that you saw in blue and red colors, those are complex models because bias is lower and variance is higher. You can see from the graph itself, it is very complex. It's going here and there, but it's trying to overfit the data. If the bias is high and variance is low, in that case, the model is a simple model. That is the green regression line that we have drawn. So what you have to understand here is, the trick is there, that main trick that is there in the way you balance out between bias and variance. If you increase bias, that's a problem. If you increase variance, that's also a problem. So you have to find a sweet spot somewhere between a simple and complex model, where bias is also somewhat adjustable, variance is also somewhat adjustable. That's why I told the error that you have, that is composed of bias error, variance error. So when both these errors are there in the main error, if you try to decrease one error, which is bias error, automatically I told you variance will increase, which means your total error is anyway increasing even if you're decreasing bias error. So the trade-off is finding the sweet spot where bias error is also minimal and variance error is also minimal. And what is the trick that you use for it? Main trick that you use is regularization, because when you do regularization, it helps you in controlling the bias variance trade-off. And once you control the bias variance trade-off, that helps you in building models that generalize perfectly with new unseen data. The whole point is that, see, whatever data that you already have, you can fit to it. But why are you preparing this model at all? Why are you making a linear regression model or any model for that sake? The reason you're making that model is that when you give any new data sets, the model should be able to predict correctly. So for that, you need that the model should not underfit, it should not overfit. That's where the bias variance trade-off comes important.